This video is addressing trigonometric functions. So we have three main trigonometric functions, sine of x, cosine of x, and tan of x. We're going to talk mainly about sine and cosine in this video, and just a little bit about tan. But two major things to do with trigonometric functions is the amplitude of the function and the period. So the amplitude of the particular function is half the distance between the maximum and minimum value for sine and cosine. For tan, the amplitude is actually irrelevant because it goes on forever. Each of the sections of the tan functions go on forever. So the amplitude is irrelevant. However, the period is relevant for both sine, cosine, and tan. And it's looking at how long it takes to complete one full cycle. So the standard period for sine and cosine is 2 pi or 360 degrees because it completes one full cycle within 2 pi or 360 degrees and then repeats over and over again for each lot of 2 pi. Tan, however, repeats after 180 degrees or pi. So we'll talk a bit more about the tan function later, but to calculate the period, we do 2 pi over b, and b is the part of the formula you can see in this slide here. B is what comes before the x in the sine and cosine formula, and the a at the beginning of the sine and cosine equation is the amplitude. C and D are transformations, so just like ordinary functions, C is shifting left or right, horizontal translations, and D is moving up or down. You can see here I have drawn or given you an example of what the sine function, what the generic y equals sine of x looks like. You can see it starts at 0, 0. The highest value is 1, the lowest value is -1, and then it starts to repeat again at 2 pi. So the amplitude of this function is 1 and the period is 2 pi. It's the same with the cosine value. However, you can see cosine starts at 1, dips down to -1 at pi, and then goes back up to 1 at 2 pi before it repeats the cycle again. We'll have a look at sine now to look at how the amplitude has changed. So compared to the graph on the previous page with the red line there, the sine value, you can see the maximum value is 1, the minimum value is -1. However, when we look at this one, our maximum value is 3 and our minimum value is +3. So what that means is the transformation that's happened is the amplitude is now 3. And all that means has happened is we put a 3 in front of the entire function because every value along that function has been multiplied by 3. You can see it hasn't been moved left or right. It hasn't repeated an additional cycle within 2 pi. It's just the maximum and minimum values have changed. So the formula for that one is, or the equation is, y equals 3 sine x. So I've just written there that there's no change to the period or any translations. If we have a look at the next one, however, again, it's a sine function, and you can see now it's completing quite a number of the cycle within 2 pi, and you can see it stops here. It starts to repeat again. So you can see it does 1, 2, 3, 4 cycles within 2 pi now. So we can see here the amplitude is the same. So amplitude is still 1. However, if we look at the period now, so the normal period is 2 pi for sine x. So period of sine x is 2 pi. However, we can see that the first time this graph repeats is where I circled here, where I first put that cross in, and that is halfway between 0 and pi, which means it is now pi on 2. So the period of this particular graph is pi on 2. So when we're trying to calculate what b is, which is the value that we're going to put in here, we know that to calculate the period is 2 pi on b, So we've got our new period here. So then all we would need to do is we would solve this for b. So we would move, if we move the 2 over, we get 4 pi on b equals pi. And then if we divide by, we swap the b and the pi around, we would have b equals 4 pi divided by pi, which of course they cancel each other out. So we're left with 4 here. And you can see that it does 4 cycles within that 2 pi value. We'll have a quick look at cosine of x now. Similar properties. If we look at this one here, normally cosine would go through 1. You can see now the maximum value is 2 and the minimum value is -2. So our amplitude has changed. Amplitude is now 2. So we would have 2 cos x. Again, period is the same and there's no translation. Okay, so period is still 2 pi because there's still only one cycle being completed within 2 pi, and the graph hasn't been moved up or down, left or right. If we look at the next one though, same again, the amplitude I've left as 1. So the amplitude is the same, that's why there's no number before the cosine. However, we are missing our b value here. So if we have a look at how many cycles this one completes, you can see, here is where we would complete 1 full cycle, then we've got another one and another one. So we're actually doing 3 cycles within the period of 2 pi. So again, if we have our calculation for b, we would have 2 pi on b equals 2 pi on 3, because you can see, I'll just circle it there for you. That point there is where it starts to repeat again. So if we do our calculation again, if we multiply, we would have 6 pi on b equals 2 pi, and then we swap the b and the 2 pi around, so we would have 6 pi on 2 pi equals b. Pi's can cancel out. 6 divided by 2 is 3. So b is 3. And again, if we have a look, we've completed 3 cycles within that 2 pi, which is why we say there's been 3 cycles, but the period is now 2 pi on 3. The last thing is the tan function. So you can see here the green line on the graph is what a tan function looks like. The blue dotted lines that I have drawn on here are the asymptotes. So amplitude is irrelevant, which is what I talked about before. You can see that we can see a full cycle within the asymptotes, which the asymptotes happen at 90 degrees and 270 degrees, or pi on 2 and 3 pi on 2, because the cosine value is equal to 0. Because if we remember the tan calculation, the value of tan comes from doing the value of sine divided by the value of cosine. And of course, we can't divide by 0. So anytime cosine is 0, it'll bring up an asymptote on the tan function. So we have a period of pi with tan. The amplitude is irrelevant. To check what the a value would be if we had y equals a tan of x, we always know that tan of pi on 4 or tan of 45 degrees is equal to 1. So if we're looking to see what the dilation is by trying to work out that a value, we could look at where that value of 1 now sits, or where that value on tan of 45 degrees or pi on 4. If it was at 3, for example, we would then have y equals 3 tan x. So that's just a real simple summary about our trig functions and about amplitude and period.